Where do we focus the search for valuable ore deposits like gold and copper? That's a multi-billion-dollar question that Emeritus Professor Stephen Cox's work over the past few decades has helped answer.
We are not particularly good at exploration. We can find where ore deposits outcrop the Earth's surface, but we've got most of those now in most parts of the world. So we need to find deeper deposits.
Finding those deeper deposits requires a fundamental understanding of how they're formed. Professor Cox is a structural geologist who studies the interaction between processes of deformation and the movement of metal-bearing fluids. As rocks deep in the Earth's crust are metamorphosed, they release high-pressure fluid carrying low volumes of valuable metals.
It migrates out of that bulk volume of material. Then if there are faults which are forming, the flow localises into those structures and gets transported via a short-circuit pathway basically towards the upper crust. And there, because we're rapidly changing temperature, reducing pressure, and also the fluids are flowing through rocks with different chemistry, that chemistry can then scavenge the gold out. And if chemistry works right, we can get an ore deposit. If it doesn't work right, we don't get an ore deposit.
Earthquakes play a significant role in forming ore deposits by enhancing the permeability of those structures. As fluids migrate upwards, they can cause a buildup of pressure that triggers earthquakes, allowing the fluid to then forge new pathways through the rock. These fluid-driven earthquakes aren't the major destructive events we hear about in the news, but rather cascades of thousands of tiny ruptures known collectively as earthquake swarms.
During one swarm, you might produce maybe 1 to 10 kilograms of gold. And so we produce our many tons of gold by having thousands of such swarms. So it gradually accumulates deposits by many little flow episodes.
Because swarms recur on timescales of a few decades, this new model suggests that ore deposits previously thought to take millions of years to form could be produced much more quickly in active fault zones.
We can produce a 50-tonne gold deposit in a period as short as 100,000 years. It might be a bit longer, it might be a bit shorter, but on that timescale.
Professor Cox has seen many examples of this type of gold deposit firsthand.
Just through here are many, many grains of gold, and this is extremely rich. So this is running up maybe 50 or more grams per tonne.
Most recently, he's been studying the Fosterville gold mine just east of Bendigo to better understand similar gold deposits all around the world.
They're all behaving essentially in the same way. The fluids are water CO2 rich fluids, and the structures in each of these deposits look similar. So an insight we gained from one tells us how the others operate.
Professor Cox says he enjoys working at the interface between fundamental and applied science. He's also passionate about communicating what he's discovered to the people who can use it.
I liked the idea of working with something which was societally more relevant than just general structural geology. So I became very enthusiastic about trying to understand how various sorts of ore deposits form. And that's led me through my interesting career.
A career that has now seen Professor Cox awarded the Haddon Forrester King Medal from the Australian Academy of Science.